Terrific. Good morning, everybody. I'll have a bit to say at the end of this hall about the events of the last few days, but for right now, it's my pleasure to introduce our guest speaker. Half a century ago, John Horton Conway, a young and brilliant mathematician, discovered a knot. This wasn't the sort of knot that one can create out of string, but rather a conceptual tangle of Conway's design, which he calculated and which became special in an area of mathematics known as knot theory. Conway's knot, one of many thousands in this mathematical realm, had one property that made it the subject of intense scrutiny. The problem had to do with proving whether Conway's knot was something called slice. Of all the many thousands of knots with 12 or fewer crossings, mathematicians have been able to determine the sliceness of all but the Conway knot. For more than 50 years, the knot resisted every attempt to untangle its secret, achieving a kind of mythical status. In 2018, Lisa Piccirillo, a graduate student and Boston College alumnus, learned about the Conway knot problem while attending a math conference. A speaker mentioned the Conway knot during a discussion about the challenges of studying knot theory. Quote, for example, the speaker said, "We still don't know whether this 11 crossing knot is slice," end quote. Ms. Piccirillo thought to herself, this is ridiculous. It's 2018, we should be able to do that. A week later, she produced a proof that stunned the math world. This morning, we are honored to have with us mathematician Dr. Lisa Piccirillo. Dr. Piccirillo is an assistant professor at MIT, where she specializes in the study of 3- and 4-dimensional spaces. She is broadly interested in low-dimensional topology and knot theory, and employs constructive techniques in 4 manifolds. And as you may have discerned, Dr. Piccirillo gained fame for proving that the Conway knot is not, in fact, slice, a term she will explain a bit this morning. After earning her bachelor's in mathematics at Boston College, Dr. Piccirillo earned her PhD from University of Texas at Austin. In addition to receiving an inaugural Mizrahi New Frontiers Prize, recognizing outstanding early career women in mathematics, she was also recently named one of Wired magazine's People Who Are Making Things Better. Dr. Piccirillo spent her COVID fall as a visiting researcher at the Max Planck Institute for Mathematics in Bonn, Germany. And we are honored to have her with us this morning. Would you join me, please, in welcoming to Roxbury Latin, Dr. Lisa Piccirillo.
Thank you. Thanks for the introduction, and thanks so much for having me. Yeah, so I was asked to talk to you a little bit this morning about the nature of doing abstract math, but maybe as foreshadowed a little bit in the introduction, I'd like to start out by talking to you about knots. So a knot is just a circle, but we're going to think about the circle as sitting in 3-dimensional space. So maybe something like that. That's a very boring circle, but you could think of it kind of floating right in front of your computer screen. Or maybe something like this. Like I don't have any firm requirements on this circle being geometrically rigid. So if you make a circle out of a piece of string, you could sort of move it around so it looked like that. So that's a knot too. And so is this. In fact, maybe this is the same thing we saw before, just with like a kink put in it, if you imagine this was actually made of rope. And all of these are knots too. And in fact, anything you can build by going down into your basement and getting an extension cord and making a huge mess out of it and then plugging the ends together, that's a knot. And so when mathematicians study knot theory, these are the objects that we're going to be looking at. It turns out to mathematicians, some knots are in fact created equal. So mathematicians say that a pair of knots are the same if they can be wiggled around in space so they look exactly identical. So if you build a knot with your extension cord and your friend builds one, if it's possible to move yours around so it looks just like your friend's, then we say those knots are the same. And so there's some knots on this screen that are in fact the same, right? Like if you build this really boring, really round knot, and then your friend builds this one, like, well, fine, you can wiggle those cords to look like each other. And this one too, right? You could just sort of untwist that kink and it would look just like the first one, say. And in fact, this one too, right? So this one's slightly more complicated, but you could imagine taking maybe this strand of this guy and pulling it sort of down so that it didn't have to touch itself here and here. And this starts to look simpler. And you can maybe finish checking on your own that indeed this can be wiggled to look exactly like this. But not all knots are the same. So for example, if after this you get out an extension cord and you build this knot here and you start getting the wiggling, try to get and you try to get here, it's not going to go very well. This is actually not possible, and this is not possible to turn this into any of these either. So we do have sort of more than one type of knot. They can't all be wiggled to look like this. So unfortunately, perhaps, well, sorry, let me start by giving you a little bit of language. This very boring knot here is something called the unknot. And since these other guys are the same as that one, those are also all the unknot. And because this talk is virtual, we can't actually like stare at extension cords that I wave around in the room. So we're not looking at a three-dimensional picture, we're looking at a two-dimensional picture on our screen, right? And these pictures are something called knot diagrams. And I want to emphasize that they're just a picture of our knot. Our knot is really this object sitting in 3D space. So our diagrams have these special bits, which are these parts where I show you that in space, one part of the cord is crossing over the other one. And we call these special bits crossings. And what I want to spend the next few minutes talking about is a question I think that comes up really immediately when you start to think about knots and crossings, which is whether starting with any knot, any crazy thing you can build out of an extension cord, it might not be the unknot. We've seen that this one and this one maybe aren't the unknot. The question is, could you turn them into the unknot if you were allowed to change crossings? So somewhere where you saw the extension cord looking like this, if you were allowed to just, by a bit of magic, turn it like this, could you get your knot to turn into the unknot? So I want to try to study this a little bit. And to start out, I just want to look at a couple of examples to sort of build some intuition for whether this should be true, and if so, like, how should we understand that? So let's look at maybe the first non-trivial knot on our list and just try to change a crossing. Maybe we try to change that one that I highlighted in yellow. Okay, there's the change. So I switched this strand, which was over before, now it's under. And now this knot here, this maybe looks familiar. This was the fourth knot on our list before, and we actually already saw that knot can be wiggled into the unknot. So this sort of fifth knot on our list, it wasn't the unknot to begin with, but you can change a crossing and get the unknot. Okay, but that's just one example. We'd like to know whether this is always possible. But towards building intuition, let's just check maybe one more example. So here's the final knot from our list. And again, if we change maybe this crossing in yellow, so there it is, it's been switched. Now we get this thing, which still looks kind of complicated. So we want to know whether I can wiggle this around in space until it looks very, very boring. And I think we can. So what I want to look at is this part of the knot right here, this arc that I'm tracing with the mouse. It sort of goes over everything, right? And so what you could imagine, remember, this is made of an extension cord. You could grab this sort of over part of the extension cord, and you could just like pull it over into the left. And it's not going to snag on anything when it does that. It's sort of free to move because it's over forever. And if you do that pull, maybe what you see is something like this. That arc is just over here now. And now this picture is starting to look a lot simpler. Now it kind of just has some kinks in it, and I'll let you finish checking that from here you can wiggle a little more and get down to this picture. Okay, so it's starting to seem like maybe at least for a couple of examples, we can start with any knot and turn it into the unknot with crossing changes. And in fact, this intuition is correct. It is always possible. But all we've done so far is checked a couple of examples. So what I want to try to do now is argue that this is always going to be possible. And I'm not going to be able to check that by just checking examples, right? In fact, there's infinitely many knots. We'd be here for ever and ever if we just tried to do it for all of them. So I'm going to have to try to make some argument that says, no matter what knot you pick, this is possible. So let me try to do that. So if you want to turn a knot into the unknot with crossing changes, what you should do is start with some knot diagram. So I've put a knot diagram up here, but I want to emphasize that this is just an example for illustrative purposes. I'm not really going to just argue for this example. The argument I'm about to give works for any example. This guy's just here to help us visualize what I'm saying. So you start with any knot. And you pick a starting point somewhere on the knot, like there. And you start going for a walk along your knot. So you're walking along and everything's going fine. And then in the picture, you come to a crossing. And I want you to do something at crossing. So here's what I want you to do. When you come to a crossing, if you've never been to that crossing before, I want you to make sure that the strand you're standing on, so like we walked along this strand, we're on this strand, I want that to go over. And if it's not currently over, then do a crossing change to make it go over. So here we would do this. So I've changed this crossing so that now the strand I'm walking along goes over, and I put an orange dot here. That's just to remind me that I've been to this crossing now, because I'm sort of forgetful and it matters whether we've been there or not. Okay, so let's keep going. You walk along and you come to this crossing. We haven't been here before, but the strand I'm walking along is already over. So I'm not going to worry about changing this crossing. I'm happy. We'll just keep going. We'll just put a little record that now I've been there. Okay, we walk along and now we come to this crossing and I haven't been here, and the strand I'm walking along here is under. So I don't like that. I'm going to change it and record that I've been here. Okay, so we're getting the hang of this, right? We walk along. This is a new crossing, but we're over, so we're happy. No change, just a record. Keep walking. New crossing. Now it's under. I don't like that. I'm going to change it. Great. New crossing, but we're over, so we're good. And now we come here, and this is a crossing I've been to before. So the strand I'm walking along is under, but that's okay. This is not a new crossing, so I'm going to leave that alone. Now we're at a new crossing again, but the strand I'm walking along is over, so it's good. Oops, sorry, that's the record for up here. I got ahead of myself. So here's the record for down here. Okay, we walk along. Now this is a crossing I've been to before, so it's okay that it's under. This is a new crossing, but we're going over, so we're happy. There's the record. And now we've been here before, been here, been here, been here, been here, been here, and we're back at the beginning. Okay, so let me say something about what we just did. What I just did is told you a set of rules. In fact, in math, this is called an algorithm. I told you an algorithm for starting with any knot and choosing some way to change some of the crossings in this method I've described by going for a walk. So what are we trying to do? We're trying to understand whether, given any knot, we can turn it into the unknot by doing some crossing changes. And what I did is I said, given any knot, here's a way to change some crossings. So what I should try to convince you of now is that I've actually changed this thing into the unknot, which shouldn't be immediately obvious. Like this knot here, you know, it's different from what we started with. We changed some crossings, but it still looks kind of complicated. So I want to try to argue that, in fact, this guy is the unknot. We could wiggle it to look very boring. So to do that, the first thing I want you to do is give yourself an extra extension cord near the starting point. So what I mean by that is maybe do something like this. This is just to give you a little more space. If you want to just imagine that your original extension cord was in fact like a bungee cord extension cord, then you could just stretch it out right here. Okay. So now I want to sort of look at this picture from a slightly different perspective. So right now, right, the knot is a thing in 3D space, but you're looking at a picture of it in your screen. So maybe it's reasonable to think about like the knot in 3D space. It's kind of floating in air right in front of your screen. And the parts where you have an overstrand, those are a little closer to you. And the parts where you have an understrand, those are a little closer to your screen. So like a schematic picture of this knot floating in front of your screen might look something like this. And this green picture is just meant to be kind of, it's not a literal picture of this knot up here. It's just, you know, your knot looks something like this in front of your screen. Okay, so fine. Now we're going to try to understand that this knot can actually be wiggled until it looks very, very boring. How are we going to do that? What I want you to do is I want you to grab this point right here and pull it towards you out of the screen. Okay, so let's try to imagine what will happen to our knot when you do that, when you pull this thing towards you. To this kind of new extension cord bit, like everything's going to be fine. You have like a big kind of coil here. You have lots of space. So the new extension cord is just going to like straighten right up. It's going to be fine when you pull this out of the screen. But what about the old extension cord? What about, you know, this part that kind of came from our original knot? What's going to happen when I pull this point out of the screen? Well, actually everything's going to kind of be great, right? It's just going to lift right up. And that's because of this walk thing we did. We changed these crossings so that when you come to them, you're always over first. So when you lift this point up, everything is going to be completely free. It won't snag on itself. So when you lift this point up, maybe down in the bottom of the page, the schematic, you'll see something like that happen. Okay. And now that is kind of good news. So from your perspective, looking at the screen, when you lift this point up, maybe not too much changes. But if like your sister walks in and looks at you and your screen from the side, and she looks at your extension cord, she's looking at a pretty boring circle in space, huh? It like literally looks like this. And now from here, you can certainly wiggle this until it looks very, very boring. Okay. So the next thing I want to say is like, why am I saying all of this? Why did I show up here at 8 in the morning and start talking to you about knots? What I was actually asked to talk to you about is what is the nature of abstract math? So I want to pivot a little, but I wanted to start out by talking about knots and giving this argument so that you would have an example to understand what I think abstract math is really all about. So I think math is sort of a two-part adventure. What we do in math is we define objects, and then we prove facts about those objects. And we prove facts by giving really precise, careful, logical arguments. And that's what I think I've done in the last 15 minutes or so. So we defined a whole bunch of objects like knots, knot diagrams, crossing changes. And then we showed this sort of fundamental truth about knots, which is that any knot can be turned into the unknot with some number of crossing changes. And we made this argument that here's this routine for doing the crossing changes, and look, this will always work. You'll always be able to wiggle it to the unknot. This definition of math, this might look a little foreign to you because you go to math class possibly as much as every day, and there probably aren't that many knots. And in fact, like maybe what you do doesn't really seem like the definition of objects and giving precise logical arguments about them. So let me shed a little bit of light on the disparity. What's happening in your education right now is you're doing a lot of learning objects. And in particular, one of the objects we talked about this morning, crossing changes, that's maybe more of an operation, right? Like you start with a knot diagram and then you do a crossing change to it. It's sort of an action. And you really do a lot of learning operations in school, right? Like the objects you meet are things like fractions or polynomials, and then you spend like heaps and heaps of time adding the fractions or factoring the polynomials, doing operations to these objects. So your studies right now live entirely up here. And that sort of maybe seems a bit like a bummer because this part down here, I think this is the really fun part about math. And in fact, to a large sense, this is the point. Like mathematicians don't just care about saying like, here's a thing that exists and here's another thing that exists. What we want to know is like, here's a thing that exists and here's everything that's true about it. We really want to do this proving facts bit. And in sort of a standard curriculum, this becoming the focus of a math class doesn't really happen until college. And maybe that seems a little disappointing. This is the fun part, and you don't get to do any of it or not too much of it right now. So let me say a couple of things about kind of why this is true and why education is structured like this. And to say this, I really like to think about learning math as being very similar to learning a language. So let's suppose you wanted to read The Idiot by Dostoevsky, and you really wanted to like carefully understand this literary work. You wanted to understand its context and sort of everything about it. You know, the first thing you would have to do is you would have to learn Russian, and that would take a long time. And for a long time, it wouldn't seem like it had that much to do with Dostoevsky in particular. But in order to really, really deeply understand the literary work, you have to do all of this legwork first. Another Another thing I think is really helpful about thinking about learning math as being similar to learning a language is that it helps us dispel a really common myth, which is this myth that there are like math people or math geniuses. So if I had walked in here this morning and said like, good morning, kids, like what I'd like to talk to you about today is the fact that any knot diagram can be turned into the unknot diagram with a finite sequence of crossing changes. If that had been the first thing out of my mouth, you would have thought maybe like, geez, I would like to go back to bed. And also like maybe a lot of you would have thought like, I have no idea what she's talking about. Like I'm really not a math person. And I think that's a really natural thing to think, because I would have come in here and I would have said this thing to you, which is ostensibly in English, and you just don't understand it. And that makes you think like you just fundamentally don't get something. But in fact, what would have happened if I'd said that is I would have just come in here and I would have started speaking to you effectively in Russian. And of course you don't understand it. You don't speak Russian yet. But it's not something inherent to you and your ability to speak Russian. It's just that you don't actually know those words. At least you don't know those words like in the language way I'm speaking them. And maybe the final connection I like to make about thinking about learning math like learning a language is that, you know, if you were really motivated to read The Idiot, okay, you need to start learning Russian. That's the only way you're going to deeply, truly, ultimately understand that book. But like, if you're really interested in reading The Idiot, you could also maybe simultaneously read a translation, right? It's not the whole thing, but it'll start getting you somewhere. And you can start learning proofs, learning abstract math in translation. And in fact, that's what I did this morning. Like when mathematicians talk about knots, it's a little more technical than what I just said when we talked about knots. But in fact, like we can still talk about it in this translated sense, and I can give you a lot of ideas and we can make an argument. And this is a lot more possible, I think, than is currently taken advantage of. So if you found this compelling or you'd like to sort of skip to the fun part of math, I think that could be possible. And maybe you want to talk to your teachers about getting an intro to proofs class as a part of the curriculum. And that's what I wanted to talk about. Thanks so much.
Dr. Piccirillo, thank you so much. When students and faculty, feel free to submit any questions through the Q&A feature, and I will send those over to Dr. Piccirillo to answer. I have one question for you, Dr. Piccirillo. You, in something that I read that you had written, you mentioned being from a beautiful place in Maine that had very little math. So I'm interested in knowing how you came to know this and how you came to love this and where it all sort of started for you.
Yeah, it was really a lucky accident, I think. Growing up, I liked math in school, and people said like, great, you can be an engineer. That's a career that uses math, but I don't like engineering. So I thought like I would just do something completely different. And in college, you know, I went to a liberal arts college, so I had to take some math. And the professor was really encouraging. It was kind of interesting, and I took a few more classes. And towards the end of my first year, I went to a lecture that was about low dimensional topology. It was about something like knots. And that was really the spark. I just thought that was maybe the coolest thing I had ever seen. And I needed to take classes about that right now. And that's how this started.
I have a question from a student here, and it's something that perhaps wasn't directly addressed. The question is, what is slice?
Yeah, right. So I in fact, this was not in the talk. Let me try to say something about it. So, okay. So a knot, I told you what a knot is, extension cord in 3D space. A knot, okay, we have this unknot. It's very boring. It looks like a circle. The unknot has this interesting property, which is that like if you steal your mother's tablecloth and the tablecloth has a lace border, then you could think about that lace border as being the unknot, right? It's this kind of boring circle in space. And it has this special property, which is that it bounds the tablecloth. There's this two-dimensional disc, which is the cloth, that the knot is the boundary of in 3D space. And right, this is the unknot, and you could in fact twist the entire tablecloth up so that its lace boundary looked like this, but the tablecloth was also sitting in this picture somewhere. So said another way, the unknot has this property that it bounds a disc in 3-dimensional space, bounds your mother's tablecloth. So what is sliceness? Sliceness is this property that asks whether or not a knot bounds a disk in 4D space. So when we ask about sliceness, we're asking, could I take your mother's tablecloth? Or sorry, more accurately, could I find a tablecloth whose lace boundary is this knot here? However, that tablecloth is going to get to use a little bit of extra space, not just the room you're in, but it can actually sort of sit in a 4th dimensional space if it wants to. That's what sliceness is.
Thank you. I have a couple more questions coming in from students. When you were deciding what field to go into, did you ever consider applied math? And if so, what motivated you to pick pure theoretical math over applied math?
I didn't consider applied math because I only love one thing, and it's knots and 3 and 4 dimensional spaces, and that just lives within the realm of pure math. I think if I had done something other than pure math, it would be like being a journalist. I didn't really want to be a mathematician or a scientist. I really wanted to be a low dimensional topologist. So I never considered any other adjacent fields.
Another question here. Can you explain the idea of 4-dimensional space?
Yeah, let me try. So a 2-dimensional space, you sort of know what that is. You have to draw plots in it all the time, right? It's a space that's parametrized by maybe being able to go up and down and left and right in the table. And a 3-dimensional space is a space that's built out of a 2-dimensional space by just adding one more direction of movement that's allowed. So, 2D space is in the table, and you build 3D space out of that by adding one more independent direction. Now you can go up out of the table. So what's 4D space? Just do it again. Just start with 3D space and give yourself one more independent direction of motion. So you can't picture this. I can't picture this. No one can picture this. There's no magical 4-dimensional visual person. And if anybody tells you they can do that, then they're spouting nonsense. But you can formally define it. Like, just like when in math class, you have to write down, like, what is R2? It's the space of points X, comma, Y. And, then maybe you have to say such that blah, 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 because there's an equation because you're in math class. Like, you can just say, what is R3? It's a space of points that have an X coordinate, a Y coordinate, and a Z coordinate. And what's 4-dimensional space? Well, it's all the points you can get if you have an X, Y, Z, and maybe W coordinate. So it's defined completely abstractly, but what you should think about 4D space as being is like, well, the difference between going to 2 to 3, adding one more direction, that's how we get to 4D space. We start with 3 and we add one more direction.
I have a question here from a member of our math department, a faculty member. For many centuries, Euclidean geometry was taught as an axiomatic system with plenty of rigor to introduce young people to the formal logic necessary for abstract mathematics. Do you have any comment on the teaching of geometry in that way as a means of showing generally educated people what math is all about?
Yeah, I completely love studying geometry in that way. And I don't quite know why it's not done more, because it was done that way for a long time. Maybe something I'll say is that it did get really formalized a while there at the end. Like, you were doing proofs with like these columns. I don't know if this person remembers that or anyone else. Anyway, there was some formalization that happened at the end of that pedagogical movement. I didn't love that because I think math is a little more creative than just like column proofs. But yes, I think we should teach geometry and proofs much earlier on from an axiomatic perspective.
I have a question that came to me from a faculty member. Given that certain kinds of abstract math are interesting and accessible to maybe a limited number of people, why is even more fundamental math important for the rest of us to learn?
I mean, it's not. Like, you don't have to read Dostoevsky and you'll be fine. It's a thing that exists. It's a triumph of human creativity and understanding, just like literature. So it's something that's a privilege to get to study, and it can be fascinating, but you can also choose to do other things, and that's fine. I don't think we should take it too seriously.
I have another question from another faculty member. And the question is, as a researcher of math, as a professor of math, in spending your days, are you typically working on a problem, a proof, or are there many at a time that you're working on? And how does that process work for you? How long are you spending? How much of your time is success and how much of it is sort of failure at the solution you're trying to arrive at?
Yeah, those are two really good questions. So maybe the first one is that I usually have maybe 3-ish projects going at a time, though when one project starts to really get near like actually progressing, I'll maybe put the others aside and just focus on that one for a few days so I can really live with it. And how much time, what percent of the time am I being successful? That's approximately 0. So something about the nature of abstract math is like, I did something really misleading to you today. I said like, here's this problem, can knots be unknotted by crossing changes? And then I just said like, yeah, they can, and here's the argument. But what would have actually happened if I just gave you that problem and sent you home for a couple weeks? Like what would have happened is you would have tried a bunch of examples and you would have started to see that you think it's probably possible. So now you have this conjecture, yes, it should be possible, but now you have to prove it. And it's not at all clear how to make that argument. So you would just spend weeks and weeks like trying to understand why this should always be possible. And every single day, like at the end of the day, you would have nothing to show for what you thought about. Like you still wouldn't have an argument. You maybe would have a slightly better understanding of things, but yeah, it doesn't look good on paper. So that's what doing math is like, and that's something that's very hard about it. You have to be prepared to fail all day, every day, basically, except a very small number of good days where you write something down.
I have a question from John Lieb, who's the chair of our math department. And his question is, do you have a favorite non-knot theory theorem?
That's a great question. My favorite kind of theorems come from spaces doing something really weird. Like maybe you thought that like you have some objects and you want to understand some property of them, and you think like there's a finite list of possibilities that they could achieve. Like you thought about everything reasonable, you wrote down the whole reasonable list, and now you want there to be a theorem that says like the reasonable options, those are all the options. My favorite kind of theorems are the ones that say like, no, some other weird stuff can happen. So maybe an example is that I study spaces that locally look like Euclidean space. So for example, a 2-dimensional space is a space that when you zoom into it, it looks exactly like a piece of paper. But when you step back and look at it globally, it maybe looks a little different. So here's some examples. The peel of an orange is a 2-dimensional space. So if you zoom in, look at it real flat, it could just kind of lie on the table. It could be 2-dimensional. But when you zoom out, it looks like a sphere. It's not a piece of paper. And another example of a 2D space is the glaze on a donut, which again, like if you zoom in at the glaze, it's just this kind of crackly sheet, but globally it looks more interesting. It's going around a donut. So you might ask, what are all the 2-dimensional spaces? And here's a really reasonable conjecture. There's the skin on an orange. There's the glaze on a donut. There's the glaze on a donut that has 2 holes. Like if you kind of smush 2 donuts next to each other, and now look at that and glaze it, you could look at that glaze, or 3 donuts or 4 donuts, all of those for any number of donuts. And then you might think, that's it. Those are all of the surfaces I can think of. You think for a long time, and that's the full list you come up with. And it's a theorem that's not the whole list. There's other stuff and it's weirder. And I like those kinds of theorems.
I have a question here from a student, and his question is, after solving Conway's knot, which was left unsolved for half a century, how does a scientific mathematical community react to a breakthrough in a field from a younger member?
Yeah, I don't know how to answer that in full generality, but in my case, people were wildly supportive. People wrote to me sort of right away. They indicated that they thought that the techniques that I had used, which were new, would really sort of spark a movement in the field where we could start to solve some problems that had been unapproachable for a long time. In fact, they were almost too supportive, sort of suddenly, and now I'm an expert. At least people act like I'm an expert in things that until very recently I would not have told you I was an expert in. So they sort of immediately look to me for some leadership, which is something I'm trying to learn to step into.
Next question here is, how do you go about solving the quote unsolvable? What sort of mindsets and strategies help you to persist and solve really hard problems?
I think you have to think that this is not going to work, and you have to be okay with that. Like, every time I approach a hard problem, I think like, all right, this is not going to work, but I just want to understand why it's not going to work. So here's an approach, like, let's see what goes wrong. And trying something and understanding why it failed, that does progress you towards understanding the problem. So I think as long as you want to, and you're happy and you're having fun doing a lot of understanding why this approach didn't actually solve the problem, then you can work on the problem, and maybe some magical day, the approach actually will work.
Another question from a student. So we know you're early in your career, but the question is, when you feel stuck on something, that's kind of dovetails with what you just said with being okay, with not sort of answering or solving, but when you get stuck, what's your approach for getting through it? What's your advice for getting through stuck moments?
Yeah, put it down, go for a walk, switch problems. If that's not working, if you've done that for 2 weeks and you're still stuck, maybe start trying to talk about it with someone else. I do a lot of math in collaboration with other mathematicians and bouncing ideas in between each other. Even if they don't want to collaborate with you and they're just willing to listen to you for like an hour, trying to explain it out loud to someone will often get you unstuck, because you have to put it a different way to make sure they understand, and that'll help you understand.
I have another question from a student here. What do you think the role of mathematics is in the modern world? Do you think that math is meant as a form of discovery, or more as simply a form of creativity and enlightenment?
That's a really great question. It's both, but I'm really lucky, and I'm in the second camp where I just get to do it for fun and for the wonder of understanding what's possible. But in fact, math in the modern world is wildly practical, and all the time things that we discover, like academic mathematicians who are just kind of having fun in like the playhouse over here, like in fact the things we do because we're having fun turn out to be really useful. So an example is that, the stuff I study, like studying all of the spaces that can arise that look locally like a plane but globally more interesting, that's like, we're just doing that for fun. But it turns out very recently there's this huge and really promising field where people use this to do data science. When you have a really big data set and you want to try to understand it, people are always projecting it down, but you lose a lot of information. And it turns out that if you model it to an interesting space first and then project it, it's much better. So that was probably too many details, but the point is that there's both. Like, we're just going crazy and creating things for fun, but people are watching, and sometimes the stuff we generate, it turns out to be really useful, and that's very important for progressing society.
This is perhaps, you've perhaps just answered this question, but I'm going to ask it anyway in case there's more that you'd want to add. Are there any practical uses of knot theory?
Yeah, well, so what I just said was about sort of the study of these surfaces, these flat spaces. So let me give something about knots in particular. It turns out that DNA and proteins in your body are very long and very thin, and they have some attractive properties to themselves. So they they like to be near bits of themselves, so they get really tangled up in your body. And apparently the biologists find it helpful to understand the structure of the way they tangle up towards understanding the DNA and protein themselves.
Another question, have you ever had a eureka moment? And if so, what was it about?
No. So actually, this is really like on fun, I'm afraid, but I usually have like anti-eureka moments. Like what happens is, so I told you that your mindset when you work on a big problem is, or at least mine, is like, this is surely not going to work. I just want to understand why it's not going to work. So I try a bunch of things and maybe one of them does work. But you know, mathematicians are not robots. So something else that happens is you make mistakes. And so my idea is that, or my mindset is that my approach is not going to work. And when it does work, the next thing I think is like, well, I've surely just made a mistake. And so then I spend a couple weeks trying to find the mistake. And at the beginning, I'm sure there's going to be a mistake. And 2 weeks later, like I still haven't found one. And now I start to think it's right. But this was a very gradual change. And by the time I think it's right, I've kind of already known about it for 2 weeks and I'm kind of bored. And I yeah, I've known that for a long time. So that's not very fun, but I'm afraid there's no eureka moments over here.
Next question is, what organizations and groups do you work with and how much do you work on your own?
So I'm a part of a department here. You're always a part of a department, and maybe I spend 30% of my time doing things with the department. So either attending a seminar where we all try to learn somebody else's work, attending a reading group where we're trying to understand something together, or doing other activities where we learn math kind of all as a group. That's about 30%. And then the other 60% is either by myself or with like a collaborator that I want to talk to about a project.
All right, we have 2 more questions here, and then we'll wrap it up. Question is, how do you change the crossing of a knot in the real world?
Oh yeah, that's a super great question. You don't. That's very violent. Like your extension cord can't do that. So when we study crossing changes, it's actually not because we think like there's this context where that's actually possible. In fact, we're studying crossing changes to give us some notion of complexity. So I showed you the unknot. This is boring knot. That's like not complex. And then there's all the other knots. And you might want to kind of put them in a strata of like, yeah, there's this knot right here. Like it's not the unknot, but it's not that complicated. But if you wanted to try to quantify like how not complicated is it, you could ask yourself, how many times would I have to violence it to get it to be honestly boring? So this has what we call unknotting number 1. We only had to change 1 crossing, but there's knots with unknotting number 100. And so we have some like quantified way to say that those 100 crossing knots are way more complicated than this. Sorry, those unknotting number 100 knots are way more complicated than this one.
This is the last question this morning. Do you yourself know Russian? And if so, how did you learn it?
No, I don't know Russian. I'm learning French and I speak some Spanish.
Dr. Piccirillo, thank you so much for being with us this morning. Mr. Brennan's going to close us out here, I think. Thank you.
Thanks so much, Dr. Piccirillo. Thanks for reminding us that mathematics is endlessly complex and incredibly beautiful, and that for those people who are called in this direction, there's a lot of richness in what it is that one could do, and certainly that you do. Thank you for your example of that. I wanted to close today by acknowledging what wise people have said over the years, and that's that we live in interesting times. And just when we thought we've seen it all, or our public life could not be more complex, indeed we are assaulted with new realities. And I wanted to acknowledge that. As you would imagine, as I always do, I wanted to turn your attention to public affairs and to pay attention to what's going on. It reminds me of some of you, maybe even when you took the civics class, and we're always curious about the exception. What if? How about if? And I think my response would often be, well, that's not likely to happen. It's never happened in our history. And so we don't really have to worry about it. But if it did, this is the way it would go. This is where we are now. And as I mentioned to you last week, there continue to be profound divisions in our culture. And I think it's our responsibility to imagine why there are these divisions, why there is such anger and resentment, and why is there, in a more corporate, public way, the ascribing of negative qualities to groups of people in the way that unattractively sometimes we do that individually. We are at a crossroads in our public life in the United States, and although we are looking forward to the inauguration of a new president next Wednesday on the 20th of January, at the same time we realize that even though we are hopeful about him, Joe Biden, and Kamala Harris and what their administration will bring forward, we realize that the challenges that all of us face are for all of us, that indeed to change society requires all of us to be engaged and to be thinking about ways in which we can do it. And it starts obviously one-on-one. I want to call your attention to the fact that what's obvious to any of you who've been paying attention to the news is that there was a historic occasion yesterday when, for the first time in our history, a president was impeached for the second time. And I want to remind you of what that means to impeach any public official. In particular, a president means that that person is charged with offenses. Then of course, the charges go to the other branch of the legislative, the other house in the legislative branch, and that is the Senate, where a trial takes place. And we were treated to a trial last January and February in which Trump was not convicted of what he had been charged with. That had largely to do with the Republicans' majority in the Senate at that time. Now these charges will indeed go to the Senate. The question is, in some political play, it probably will not go to the Senate until after indeed he's out of office, after January 20th. But it will be interesting to see if people even bother to convict him, if indeed it's in their hearts to do that. And we need to pay attention to that and what the ramifications are. In the meantime, all of us are anxious, thanks to what happened last week at the Capitol. All of us, I think, would acknowledge that what occurred there was different from what happened in the early summer when people were protesting and part of the Black Lives Matter movement. Those were protesters. The people who stormed the Capitol the other day were insurrectionists. They were rioters. They were intending to do damage. And as we learn more about it, we realize that in fact there was an appetite for doing bodily harm to some of our chief elected officials, including the Speaker of the House and the Vice President. This is not tolerable. And indeed, our law enforcement and our Justice Department need to follow up in ways that are not only satisfying, but appropriate for the people who have threatened our system in that way. That's enough for me to say about this now. But I just did want to acknowledge it and realize it's on all of our minds. And even as we're battling this bloody pandemic, we also are distracted by this. And as part of life, it's part of what public life is these days. And I hope for all of us that we will not only find some answers, but that we'll find some peace and that we'll also find some vaccines. Thanks very much. Have a good day.